Hi, I am Omar. I'm doing integrals over general regions. In order to know this section well, we just have gonna review what we have in 15.1 integrals in over integrals over rectangles, and which we have in the beginning. If we have a surface somehow like that, and we have rectangles down here. So we can sub that rectangle into small rectangles. And we can draw we we can draw it like this. And we gonna find those points, and we're gonna use the formula is the limit of rectangles goes to infinity, and we have this the sum of the total length times the change of area. As we said, the change of area is equal change in y change times change of x of all of these triangles. There's those triangles that law lead us to this equation over here as the double integral of d, which is this region, is equal to the function f of x and y, which times dA, which is dA is equal to dy dx. Now, in this section, we're gonna see what if we have surface like that, but the down surface, the solid surface, it's not a rectangle, is general like this. Now, if we wanna do something like that, of course we're gonna write a rectangle over here, and sub that rectangle to small rectangles. Let's assume that that's the y and x. Yes, and we have the place. What we're gonna do is we're gonna add those rectangles in blue, but the rectangles on red, we don't do them. Why? Because it's not our region. So in that case, we call this region R as a general region, and we can solve for that with the double integral of region R for the set function x and y dA, which is also dA is equal to dy dx. Now we're gonna see that in our next example, and we're gonna go with the types of integrals. So we have two types of regions. This called type 1, and this called type 2. The difference is between type 1 and type 2. Here you just you're integrating the functions of gx, but here you integration this function with respect to y, which is gonna lead us to our equation over here for type 1, which is the integral over d, which is this region. Let's call it d function of xy. The limit here, because it's type 1, the limit will be dy dx, because it's easier it's gonna be easier for us to do a function with respect to x first. Now the function of that one will be the integral of d f xy dy dx for type 2 region. No, sorry. Dx
dy, because it's gonna be easier for us, because right now here we're just gonna have y as in numbers, in real numbers, while we're gonna have function with respect to y. We're gonna uh, we're gonna integrate that, and then will be easier for us to have a second double integral. And also, there's an example from the book. So let's be careful and see what is the example is asking. Now, they want us to evaluate this integral, the double integral over region x squared plus 2y dA, and D is bounded, the region D bounded by y equal x and y equal x cubed, which is and x is greater or equal to 0. We wanna know first, in order to solve this problem, we wanna know the bounded region. If we knew the bounded region, we solve the equation. Okay, let's go through. Now, so first thing we have to draw the region we have been bound. So this one, they said y equal x, which x is greater or equal to 0. So this is x, y is equal to x, and this is x cube, y equal x cube. They meet at they should meet at 101, because we know if y equal 1, x will equal 1. Here, if x equal 1, y will be 1. If x cube equal 1, y will be 1. So they should meet at 101. So we're gonna do something that's similar as we did in calculus 2, which is area between the curve. Now we're gonna integral the area that just bounded between this area over here. Now let's do this. Let's set up our integral. So let's set up our integrals and say the x is equal y is equal first. Let's do y. What? So our upper bounds, it should be the highest. It should be the highest equation. It should be our upper bounds, which is lowest our lower bound. It should be over there. So we gonna write our upper bound over here is y equal x, and our lower bound of bound over here is y equal x cubed. Now we go to the x. We know x is the area bounded. It is started from 0 as x is equal or greater than 0, and it reaches x equal 1 over here. So the area bounded in the x direction, it will be from 0 to 1. And this guy, this thing is type 1 integrals, because we have those the first integral as a function of x, so which is will make our work way easier. We could flip those together, but it's gonna be difficult in the end. So I will do this example. You will see. You will have this example with type 1. This example with type 1, but the next one we will choose type 2, and it will be easier for that, and I will tell you why. Okay, just wait, calm down. Now, so in order to evaluate this double integral, sorry, we just have to do this first. The integral of y equal the integral for of x squared plus 2y from x to x cubed. So that's integral. We have to do that first, evaluate the integral, and then we do this one. After we get the value of this thing over here. Okay, let's solve. Let us solve it and see how things will go. Now, if we have the integral from y equal x to y equal x cubed, equation of x squared plus 2y dy. Now, because our x squared, we're gonna treat that our x's, we're gonna treat those r squared, and we're gonna integrate with respect to y. So we will have x squared y plus y squared, and the bounded is and the limits of integration are x to x cubed, which is gonna lead us to x cubed plus x squared minus yeah, minus x to the 5 plus, sorry, minus x to the 6. Okay, now we're gonna put, so this value over here is just the value of for this integral. Now we're gonna do the second one, which is the one, the red, and we're gonna substitute what we got over here in there. So the bounds are for the second integral, that's why it's called double integral, are the limit of integration is 0 to 1. We have our function over here. Gonna write that again, dx, and that one we will have an answer like it will be x to the fourth divided by 4 plus x to the third divided by 3 minus x to the sixth divided by 6 minus x to the seventh divided by 7. Limit of integration from 1 to 0. We know we're gonna substitute that back, and we gonna left with, if we substitute that back, plug it in the calculator, if we substitute that back, we're gonna have 1 to the 4 plus 1 over 3 minus 1 over 6 minus 1 over 7. When we have 0, we don't care, so we just, because it will just equal to 0, so this was our answer. Plug that in the calculator, we're gonna have 23 over 84, which is area bounded by that region. This is our answer, and let's go to the second example.
Hello, my students again. We are doing this example. We're gonna find the surface, find the volume under the surface of z equal 1 plus x square y square, and above the region enclosed by x and y square. This this is just a drawing, give you an idea about this function. And we just wanna find the the volume of the surface in the surface of z equal 1 plus x square y square above the region enclosed by y equal x, by x equal y square, and x equals 4. So it's gonna be a region that's somehow is over here, and it have a volume like that, and we
want to know what is that volume. Now, as I told you, we use type 1 into the previous equation. This equation, we're going to use type 2 integral. And now we will see why. If if we bounce, if we draw up the regions, that's not steep enough. Wait a second. So we have x equal y squared, which is something like that, and x is equal to 4. For now, we're gonna have this be x equal 4, and this will be x equal y squared. Now, to set up our integral, though, we're gonna have we're gonna write our two sides of integration, and first we're gonna integrate with respect to dx and dy because it's gonna easier for us because we're gonna have the functions with respect to y, the algebra function. If now the upper bound will be like it seems the upper one, which is the one that goes toward the right, which is this one, x equal 4, and the lowest one is x equal y squared. It's similar to uh, the the area between two curves, in as we did in calculus 2. And the y bounces, as we see here, for this area, that's the y bounces is going from -2 to 2. So we're gonna put those as our limit of integration, and our function is 1 plus x squared and y squared. Now we're gonna solve this function. As I said, we're just gonna do the same thing as we did above, and we're gonna integrate this first. Sorry, sorry. We're just gonna integrate this first, and then we're gonna go and integrate the whole thing. Now we need to get the value of this. Now let's go ahead, let's do this. Now we have the integral from y squared to 4, 1 plus x squared plus y squared dx. It's easy for us to do this integral. Sorry. So it's easy for us to do this integral. So this will turn out to x plus x cubed divided by 3 and y squared, and our regions are 4 and y squared. This will lead us to into this equation, which is if we should plug 4 plus x cubed, 4 plus 4 cubed divided by 3y squared minus y squared plus y cubed, because if you plug y over here, it would be y cubed divided by 3 times y squared, and this should lead us to equations like negative y to the 8 divided by 3 plus 64 y cubed divided by 3 minus y cubed plus 4. So this we're gonna plug this integral and we'll solve for it, and this is this is the value of this integral over here. We go back again and we write our new integral, which is negative 2 to 2, which is y to the 8 divided by 3, 64 divided by 3 y cubed minus y squared plus 4. Sorry, this one is y squared, just a mistake. Oh wait, let's come back at this. Sorry, I think I did a mistake over here. Don't mind me. Yeah. So it's just it's y squared. Let's do this. Let's do this one. So we're gonna have an
answer as sorry, it will be negative y to the 8. It will be negative 3. Sorry, wait just a second. Eight divided by 24 plus 64 divided by 12 y to the fourth minus y cubed divided by 3 plus 4y, and the limit of integrations are 2 and negative 2, which is going to put us on 2 to the 8 divided by 24 plus 64 divided by 12 times 2 to the fourth minus 2 to the 8 divided by 3 plus 4 times 2 minus negative 2 to the 8 divided by 24 plus 64 divided by 12 plus negative 2 to the fourth minus negative 2, sorry, this one's cube, negative 2 cube divided by 3 plus 4 times negative 2, and this is, my friends, will equal to 2336 divided by 27, and that's the volume above the regions. And this is our final answer. Final tips: if you just could know what is type 1 and type 2 equations, and in order to that, you can solve the equation. Choose the easiest one. Don't make it difficult, don't make it tough, and you will be good.